Okay, so just to remember what we did the first class, we started looking at the linear elastostatics in 1D, and we did this because this is the simplest, probably the simplest differential equation that we can start tackling in finite element analysis, and so it is very important to understand all the procedures that take us from the differential equation, right, the equilibrium equation, to all the way down to the discrete equations that you are solving in a computer. Because if you understand the procedure repeats itself, and it's just a matter of plugging in another differential equation, and the procedure is the same. So in broad terms, you always start with your equilibrium, the equilibrium that you are trying to solve. In this case, is a balance of linear momentum, or the equilibrium equation. Then you come up with a variational formulation of that, or a weak formulation, and we do this basically to lower the differentiability requirements on the trial solutions that we're using, right? So what this is doing is basically describing equilibrium on an average sense, right? So you're not satisfying equilibrium point-wise along the bar, but you're doing this on average. And so once you have that variational form, you still need to get down to the discrete equations. So how do we do that? Well, we follow the Galerkin approach, and that means that we are coming from an infinite dimensional space into a finite dimensional space. Okay, because finite meaning you still want to solve this in a computer, right? So you have limited memory, and so we choose a space of finite size, and then as we saw the last class, like if you are choosing the trial solution and the weight function from the same space, this approach is called the Bubnov-Galerkin approach, and if not, it's called Petrov-Galerkin. Okay, but still, that doesn't mean that we have finite element equations. The discrete equations are not there yet. At this level, right, when you have your finite dimensional space, you can, for example, adopt what is called the Rayleigh-Ritz method, where you are describing your basis functions being applied over your entire domain, and this is widely done in dynamics, for example. But we still want to go a step further, and we want to basically analyze the whole domain by little pieces, hoping that the behavior, the ensemble behavior of all those little pieces are going to somehow approximate the whole. So that is, in broad terms, what we're trying to do here for the bar. What is nice is that for the bar, we are going to learn a lot of insight that is going to be helpful for going into higher dimensions. So if I look at what we did last time, well, here, I'm going to go quickly through this. This is basically our differential equation. And then we talked about boundary conditions. The types of boundary conditions that you can apply are either essential, natural, or a mixture between those. And then we formulated the strong form of the problem. That means that you are able to describe the problem, the differential equation plus the boundary conditions. This forms the strong form of the problem. And then we came up with the weak or variational form, which is basically average equilibrium satisfied along the bar. And so we ended up where we compared the bilinear form. So we also managed to write our weak or variational statement in a very abstract form that you will find here and there. Okay. So today we're going to go and we're going to analyze a couple of things of this weak or variational form. We're going to see that the error is orthogonal to the space. We're going to go into detail on that, and then hopefully by the end of the first lecture, we're going to get to the discrete equations given by finite elements. So that's the whole program for today. Okay. So anything before we start? I keep repeating, but if you have any questions, please feel free to interrupt and ask. All right. Okay. So there is one little thing that we didn't address last time, and it's, yeah, everything looks fine, but what happens when you have essential boundary conditions that are non-zero, yeah, or non-homogeneous boundary conditions? And this is something that we didn't tackle last time. And so we're going to start discussing what happens, how you can actually present your weak or variational form when your boundary conditions, the essential boundary conditions, are non-zero. And this is something you will find everywhere. So if you discuss for non-homogeneous essential boundary conditions, what you say is basically, let's say you have a function u that can be described by v plus u tilde. So you're basically composing two functions, where if you take this u tilde and you prescribe along the boundary that has prescribed Dirichlet boundary conditions, then this is your prescribed displacement field. Okay? And then v is another function from the same space that the weight function is taking. So I'll explain in a minute what we're doing here. So then the weak form or variational form becomes find v in that space that we define, such that b of u w is equal to L. This didn't change much. For all w in v0, actually it's here. And now if you replace that, right, because of the properties of the bilinear operator, these are all things that you're going to find in detail in that book chapter that I referred to earlier. Okay, all of this is very well explained, and of course, if you don't understand something, we discuss it in the nota bene, and this, again, this is very valuable feedback for me and for my colleagues. Then L minus B okay, and that is the way we handle basically non-homogeneous boundary conditions. So what did we just do here? Like, if you look at this expression where we're taking a function u and we're saying, well, that function u is composed by two parts. One part, which happens to satisfy the Dirichlet or essential boundary conditions, and another part that is actually taken from the same space where I'm taking the weight function from. So we are basically getting into the Bubnov-Galerkin approach, right? And everything boils down to find the unknown component in that space, right, that is going to be able to help us represent the entire solution. Yeah? And so normally, and you will see this like in more mathematical terms, like strictly speaking, this u is not a space, because the idea of a space is like you can compare this to vector spaces. Like if you, let's say you have a plane and then you have a vector pointing in that direction, and then you add it to a vector pointing in a different direction. If you add those two, well, you would expect that the same vector lies in the same space, right? In function spaces, it's the same. But let's say if I define this u as a space, if I take one function from that space and I add another function from that space, suddenly the function has twice the value of the prescribed displacement at the Dirichlet boundary. And so it does not belong to, this is not a space. So this is what mathematically is called linear variety. So it's basically a translation of a space so that you ensure that you have boundary conditions. But this is just very mathematical. It is still, we talked about this in the book because, well, I think it's important to realize that this is not a space, but it is really not that important for you, okay? What you see though here is that what happens when you have non-homogeneous boundary conditions? Well, something happens here because this u here is known, right? And so this whole term becomes part of your right-hand side. And so you would expect that if you have non-homogeneous boundary conditions, those are going to change your force vector when you get to solve the discrete system of linear equations. So that's how it works. As long as this u is 0, well, of course, this term doesn't do anything to the right-hand side, but the moment you are prescribing a displacement into your object, right, your solid, your domain, then that is going to change somehow the right-hand side force vector. Okay? All right. And now I am not sure whether I defined V naught, but it seems not, so I'm going to do it now. It's basically the space of functions V in, remember we did define the energy space, right? Such that the restriction of V in the part of the boundary that has the essential boundary conditions is equal to 0. So you all understand what we're doing, right? We want to use the Bubnov-Galerkin approach. That means that we're taking both the trial solution and the weight function from the same space. This is called V naught. V naught has 0 value at the boundary where we're prescribing the displacement. And so we're just expressing our trial solution in this form that is composed by one of the functions taken from this space, V naught, plus a function that happens to satisfy the Dirichlet boundary condition. Okay? I'm repeating again because I see that you're still looking at me like, okay. Yeah, but if you don't understand something, please let's talk about it. Okay. So this is still infinite dimensional. So what we're going to do now is we're going to talk about the Galerkin formulation, right? So this energy space we defined is infinite dimensional. So clearly our exact solution is going to belong to that space. Okay? If we happen to be able, let's say, to model or to solve a problem where we are taking an infinite space, of course that's not possible because our computers have limited memory. But if we were able to do that, then you would find the exact solution. But that is not possible. And so we take a finite size of that space, right? And then we agree to the fact that there's going to be some error. Yeah, our solution, our trial solution is not going to be exact anymore, unless, of course, there are certain situations where you do find the exact solution because the trial solution happened to be in that space that you chose. But in general, this is not going to be the case, and there's going to be an error. Yeah, and now the important thing to know in finite elements is like you should be aware of that error, and you should be able to control how it decreases when you refine your mesh or when you add more functions. As long as you know what happens to the error, right, then you are in good shape. Otherwise, you are just basically using a black box, and then you're just getting some stress field that represents something, but you're not sure whether it's correct or not. Okay? And so that means basically that our solution for the case of the bar can be represented with an infinite number of bases, where this guy here is a basis that spans the energy space and this guy is degrees of freedom. And from now on, I normally call this DOFs, common terminology in the finite element world. Okay. Now, instead of doing this, we relax that requirement. By looking for a solution in a finite dimensional space. And normally, when you see we're already talking about finite dimensional, you're going to have the superscript h. That means that you are already in a finite dimensional. Yeah?
With this requirement, do you mean that E is infinite dimensional or the factor of its basis functions?
So you have an infinite number of basis functions. So of course, you would expect that if you're spanning a space with an infinite number of functions or different types of functions, then you would find your solution, your exact solution there, right? Some combination of those functions are going to give you the exact solution. Yeah.
So this points to the infinite.
Sorry.
The word this points to the infinite number of the infinite.
Yeah. Yeah. And so this EH is basically a subset of E. And we accept, as we said, that there may be an error. Yeah, so then the finite dimensional form of that equation that we just described it's find UH belonging to EH such that B of UH is equal to L for all WH in. Yeah, and so this is our statement. You see that nothing changed from before, except for the fact that now our space is reduced. Yeah, and so we can span that space with a few basis functions. Yeah, and then depending on the number of those functions, we're going to arrive to a discrete system of equations that we can actually solve in a computer. Yeah, and as we said before, if UH and WH belong to that space, this is called Galerkin. Yeah, otherwise Galerkin. Okay, and Galerkin formulations are not very common, except I've seen their use in fluid dynamics, right? Okay, so let's describe what happens with this error. Let's see how we can get some progress to understand what's going on here with the error. So we're going to look at the orthogonality of this Galerkin error. Yeah. So if you remember the first equation, the infinite dimensional equation that we wrote, we had B of U So this is the equation, the infinite dimensional equation. But I can write this, I can put WH, because of course it has to be valid for all WH, and WH is actually a subset of the infinite dimensional space, so we can still write this equation, right? You see? I'm going to put here, just for completeness, since EH is a subset of that Euler space. And if you remember the finite dimensional expression that we just wrote, this is also true. And so if you take the second equation and you subtract to the first one, right, what you get is B. Let's put a, I don't know how we do this. Let's put a sign here. I'm really not good at making straight lines. U minus UH, and then WH, the right hand side of both, of course, is the same, so this has to be valid for all WH. And what you see here is what we know as the error, right? If you take your exact solution and you subtract your approximate solution, of course you are left with an error. And this equation is very important, right? Because you can interpret this equation in many different ways, right? One way is that this is basically orthogonal to the entire space. Remember, this equation has to be valid for all WH in that finite dimensional space. So this basically means that the error is orthogonal to that space, right? In the sense of the bilinear form, right? If you can think of the bilinear form as some sort of a dot product, if you will, between functions, it is not that. We define already what the bilinear form is. But just to make the analogy to vector spaces, right? If you look at this equation, if you take two vectors and the dot product is 0, well, those two vectors are orthogonal. So this is the same thing in function spaces. In the sense of the energy norm, right? The error is orthogonal to that space. So this is one interpretation to that equation, right? So let's say if you do let's do the analogy properly. Let me just change color. And let's say this is your exact solution. So this is UH, this is U, and so this guy here is U minus UH. Yeah. So another interpretation, of course, this is just an analogy. Remember that we're dealing with function spaces, so this has to be very clear, right? But it's just to make the analogy with, because we can see this. We are very familiar with vector spaces, with the Euclidean vector space, right? And so if this is the subspace, of course it's an infinite plane, right? But take it as a in this case finite size. What you see here is that what we're doing with the Galerkin is basically we're projecting the exact solution into that space. So this is another interpretation of what's going on. All right. So we said, well, the error is orthogonal to that space. Well, you see that indeed U minus UH here is orthogonal to that plane. Or you can see, okay, I'm projecting U to that plane, in which case that's what the Galerkin is doing. So the fact that this weak or variational form has to be true for every single function in that subspace is basically trying to project. It's basically taking the component, the useful component of the exact solution that belongs to that subspace. You understand this? Yeah? And so let's write all that down. So I'll put this somewhere else. Error is orthogonal to subspace and this is of course with respect to the bilinear form. UH is the projection of U into and then there is this one from all those functions that are part of EH. UH is the one that minimizes the error. And in the book chapter that you will find in Nota Bene, there are a couple of other theorems that you are going to read, where there is something called the Thea's approximation theorem that is basically generalizing this idea to non-symmetric forms, right? In the case that we're dealing right now with the book of Galerkin, if it just happens that you lose symmetry because you're choosing functions from different spaces, then you can extend this idea, the fact that UH is the one that minimizes the error, and that is a theorem, Thea's approximation theorem, and this you will find in the book. Okay? Yeah?
I had a question about the above line, where you said that the first line is bilinear error and also the subspace of the energy power h.
Yeah.
Because the energy power h is also subspace of normal. I don't get that.
So if I understand your question, you are asking this: how can I write this?
Why is it also a subspace of?
Yeah. Okay. So let's write this first function: bu comma w equals lw. Right. This is our first infinite dimensional weak or variational form. Infinite, right? Now all w for all w in the energy space, we're talking about infinite number of equations. So clearly the equations that are found in EH here are contained in that infinite dimensional space. That's why I can write this is also valid, because if it is valid for every w in an infinite dimensional space, it has to be valid for every WH in that finite dimensional space. You understand? And that's how I can write this equation, because EH is a subspace of E.